Welcome back, DevGod here, back with another video, and today I'm going to be teaching you guys how I solved LeetCode 960, delete columns to make sorted 3. So this is a pretty cool problem that used some dynamic programming and also uses longest increasing subsequence. When I was like first going to try this problem, I was kind of being a little bit of a dumbass and like trying to make it more overcomplicated than it had to be. So I was like trying to do like, to pick a column, to not pick a column, to basically like backtrack through it, which just was not fun. It was not working out. But yeah, this is the way to go. This is, I think, like probably the easiest way to solve this problem using it longest increasing subsequences. So basically, for those who don't know, this is what longest increasing subsequence is. Traditionally, you'll most of the time see it with like numbers and stuff where you want to have these numbers and then at each position return how many places or how many subsequences or what the longest subsequence is. You want to return what the longest subsequence is at a given index. So if you were to consider this whole array right here, the longest possible increasing subsequence you could have would be 1, 2, 3, 4, 5, 6. In fact, I think I have a good. I have the longest increasing subsequence LIS located right here. So, for example, you could have like 1, 2, 3, 4, 5, but then you can't have 0 because then that wouldn't be a strictly increasing subsequence. So, for example, this right here would be a valid subsequence. This right here would not be a valid subsequence. But then you could do something like 1, 2, 3, 4, 5. Skip the 0 because you're allowed to like pick and choose like indexes in between to delete for it being a subsequence. And then you can just choose 6. Bada bing, bada boom. You have a valid longest increasing subsequence right there that's valid. And then its length just so happens to be 6 because there's 6 numbers. So that's like kind of like the main idea with traditional longest increasing subsequences. It's a pretty standard dynamic programming kind of template that some of the LeetCode problems use. And then it also matches our problem right here because we want to have some kind of sequence where we could delete characters like in between, aka we could delete columns and then return like a different subsequence. So for example, the one that I used when I was like programming this was cat, dog, and ABC because, nice 3-letter words. It's pretty easy to use. We should also probably discuss like what this problem even means. So this problem right here, what this problem is all about is you want to be able to like delete columns and then have each string be a sorted, a lexicographical string. So for example, right here, cat would not be a lexicographical string because because A comes before C, so that would be like an invalid pair. Dog would also be invalid because G is supposed to come before O, so this pair right here would make that bad. But then you could have something like ABC, where this one is actually going to be a lexicographically sorted string because A comes before B and B comes before C. So basically, it means like the letters are either in order, or you have something like A, where all of the characters are the same exact character. Um, and then of course it's like all lowercase, so you have like a little bit of an easier time there as well. So yeah, we have these strings. We want to return the minimum number of columns. It's gonna say like return the minimum possible value of an answer dot length, but basically we're not actually storing indices eligible for deletion. We're just storing the length. Well, in our solution, we're storing like the longest increasing subsequence length. But yeah, we're not like actually storing the indices that the columns could be deleted at. So basically we have cat, dog, and ABC. So one possibility could be for this test case right here, we delete the first column, and then we would have to check if now all of these strings, like each individual one is lexicographically sorted. So AT, that one's okay. BC, that one's okay. But then OG, that one's still an invalid pair. So we're going to say that's invalid. So that wouldn't be a valid way we could do it. But on the flip side, what we could do is we could delete this column right here in the middle, and this is like the intended column you're supposed to be deleting, even though we're not storing the indices that you're deleting columns at. You'll have CT, that's correct. We'll have DG, that is also lexigraphically sorted. And then we'll have AC, so that is also lexigraphically sorted. So this right here is the column that you would want to have deleted. And then basically what you also see, and then this is where we get into longest increasing subsequence territory, is if we were to compute this out, where each character basically of each individual string is included with the calculation, we'll have at the end a longest increasing subsequence of 2. That means we can delete this column, and then CT is true, so this is correct. DG is correct. AC is correct. So therefore, the longest subsequence that we can achieve on every single string by deleting one column would be considered 2. Right. And then basically this right here is just kind of the basic outline of how longest increasing subsequence is calculated. So first we're starting everything out equal to 1 for each cell of the longest increasing subsequence array. And then the big difference here, of course, is we're doing this like by column pair, not just by like an individual. So there's other problems where you would just have the word cat, but then basically you're comparing C, D, and A with that A, O, and B. And I have a better example right here. So for example, at one point you could be pairing the C and the T with the D and the G and the A and the C. So you're comparing like these two characters with those two characters using like some kind of 2-pointer thing. And then also later on you would have this where you're comparing the AT, the OG, and the BC, and you're just seeing like what you're able to do. Like if everything, so specifically in this we use an array every, but you're basically checking if everything would be a valid pair for that. And then you can increase your longest increasing subsequence, like index little position that you're evaluating. Otherwise, you're just keeping the max of. So basically, I'm probably not doing a good job of explaining this, but basically the TLDR of this is that the longest increasing subsequence is on steroids right now because we're comparing every single string in the given array versus just each pair like in an individual string. We're actually comparing like multiple different character pairs at once as we're shifting our pointers around. Other than that, we're also just checking if it's 'cause it's not like a strictly increasing subsequence or a strictly like longest increasing subsequence, so I do like add the little addition that could be like less than or equal to is the thing that we're checking. And this just shows some of the pairs. So this wouldn't be a valid pair because C and A, or C is not less than or equal to A. But then one of these, oh yeah, I think it's this one right here would actually be a valid pair. And then that's where C is less than T, D is less than G, A is less than C. So therefore, we can do some dynamic programming and mark like LIS of 2 to be either itself or like 0 because we're testing the left column at that point. So this test case right here is basically, that's how it looks like when we're testing it. Like I have like an L pointer right there and an R pointer right there. So that's how this looks right here. And then we're just updating the score with the max of. It's a little tricky to think about, but basically this right here, you can see that there's like different paths you could take. So for example, you could say 0 and 6 is a valid subsequence. So you could 1 plus 1 to get 2. But then you could also say, hey, wait a minute. 5 plus 1 is equal to 6, which is a larger number, so you would actually want to return 6. So that's like kind of the thought behind like why you want to use maxes and shit like that and a longest increasing subsequence. But yeah, and then of course like the last thing that we want to do in this solution is we want to take the string length, which is aka the amount of columns that are going to be available here. So we have column 1, 2, and 3, so 3 columns slash length, that's going to be a length of 3. So we're going to say that the answer is actually going to be 3, and then that's going to be minus our maximum, our max of our longest increasing, man, I like suck at drawing with the mouse. Oh, the maximum of the longest increasing subsequence So in our case, that's 2. So that's going to be 3 minus 2. And then that's going to be equal to 1, which basically means that 1 to go back here is because this column right here is the one column we want to delete. So therefore, at a minimum, we just need to delete one column and call that the answer. So anyway, to get to the code side of things, here's just like a standard implementation of longest increasing subsequence. You can find it on Geeks for Geeks. They have like a pretty good template there available. Otherwise, if you solve LeetCode 300, it's basically the beginner introduction to this problem. And then what we can do here is we just use 2 pointers. We check everything from pointer R to pointer L to see if it's like a valid pairing. And if it's a valid pairing, that basically means it's increasing. So the right is greater than or equal to the left. So this is increasing. So this is an increasing pairing, basically. Otherwise, we're going to check, and then if that's valid, then we can update our LIS. And then this one right here at the bottom, that's just going back to what we said before. We're taking total column length slash amount. Really, it's more amount of columns, really. Amount of columns present minus the max of LIS. And then that maximum or total amount of columns minus the max of LIS is going to therefore equal the minimum amount of columns that need to be deleted. Yep, and that's like misspelled, so let's put an L right there. Yeah, so that's like the basics of this. Otherwise we have n, that's just amount of columns. So pretty cool. Very hard problem, but then when you relate it back to longest increasing subsequence, I think it starts to make sense. But I'm probably not explaining it that well. It's been a while since I made a YouTube video. I also see that they're missing the 5th constraint, so that's pretty interesting. But yeah, other than that, they give you some like pretty good examples to follow. And I should note that there is a way to do longest increasing subsequences using like a binary kind of search approach in like n log n of time. So there is a slightly more optimal way of doing this without relying on basically a nested for loop. But the big thing here is that you have 100 or less strings as the constraint size, and of these 100 strings, the smallest column size that you could have would be 100, and they also only consist of English letters, or lowercase English letters, I should say. So basically, because at most you could just have like a 100 times a 100 thing. Time complexity wise, I mean, I'm not going to go through the hassle of implementing a binary search with that small of a programming constraint. Otherwise, what we can do is I can show you guys this running. Yep. So you can already see that's at least for JavaScript solutions. That's beaten like 100%. We have 62 megabytes, which is kind of but memory is probably like evenly split with JavaScript being an interpreted language on Node.js. And there we go. We got that sweet n squared times m, but with small problem constraints, so that's like not even an issue of concern at all, at least for us. But anyway, yeah, so thank you guys for watching, and of course, if you like this video, make sure to like and subscribe, and see you guys next time. Peace.